Uh, yes, class. So we have to start with motional EMF. So in EMI, we have completed when we were discussing the portion of induced current and the direction of induced current. That portion was done. We have done all the numericals, and I have given you good questions also in the homework. So are you or have you all attempted the homework portion? Because see, homework here it is important. Here in this portion, homework is important because lots of questions are given from that. Okay, so Rishita, Siddika, Sufyan, Zaina, very few students today. Okay, let's start the class. Then I think time is already there. Started. Okay. See, motional EMF for understand movement, just understand this. These are three rods which are constructed in this manner. Okay, one, two, three. Means the three rods are forming U shape. One end is open. This see if this is something and you are sliding it like this. Okay, this is the case. You are sliding it. Sliding what? Sliding. Suppose this is there. This is a rod. These are the ends of the rod, and through this you are sliding over it. So the distance here is x. This is the length of the rod, and this is moving with v velocity. Okay. Now, see, now in this circuit, EMF from the term is also not difficult. Motional EMF to identify is also not difficult. What is meant by emotional EMF? If you see the question, you will see everything is very straight and simple. So in motional EMF, you have this rod. This rod is moving with velocity v. Okay. Now what you will see? Now when you are moving it, over the track, EMF is also moving. That is called motional EMF. Means you cannot say the velocity of the potential is something else. No. In your circuit, there is a motion. Nothing is static. Quantities are moving. The rod is moving on this. Now the potential that is generated under the motional conditions. See, when you see that this EMF, this is moving, and you can see that in this entire setup, since the rod is being put, the rod is moving. So when you see the rod is moving, then in that case, the EMF which is generated, because it is present in a condition where movement is there, that's why it's called a motional EMF. Now, what's the definition of a motional EMF? The EMF induced across the ends of a conductor due to its motion in a magnetic field is called motional EMF. So in motional EMF, you don't have to make things up. In motional EMF, you don't have to sum things up. You just so now what you have to know, if you know what is EMF, you know now the conductor is moving. If the conductor is moving, so we are naming that this is the motional EMF. That's it. Nothing new in this. Your conductor is simply moving, and that's the simply your conductor is moving and nothing else is. Okay. So this is the figure. X is length of the loop inside the magnetic. Students are joining. Class, write it till here because many of you are joining because I have to repeat it then. Then I'll show the derivation, very small derivation. Okay. Now see when we I hope everyone is now here. Sidra, Zaina, Yahya, Siddhika. Siddhika was already there, Maria. Okay. See, how will we start this derivation? You know what is the formula of flux? It is BA. So flux BA, this area can be written as, now see, this is L, this is X. So what is the area covered by the rod? It is L into X. Okay. Now you know the formula of EMF is rate of change of flux minus d phi over dt. So this is minus dBLX. Now we can put the value of phi over dt. So minus BL, we can take it out common because magnetic field will remain constant. The length will remain constant. These two things will remain constant. X will be changed because see, this is the rod. If we are bringing it, so value of X can change. Length will remain fixed. See, if I'm moving it, this value from here. So this value can change. Length will be fixed. And what are we left with? Dx over dt. So see, what is dx over dt? It's the velocity. So what is the final formula? E is equal to, now C class, here when we are talking about velocity, we will put the formula as BLV only, not minus sign. Why? Because for us, velocity is minus dx over. What is this negative sign telling you? Negative sign is simply telling you that velocity is in the direction where EMF decreases. That's it. So what's the formula for us that we have? Formula of EMF is, motional EMF is BL. Let's see what is the meaning of each symbol. E is the motional EMF. This is a short topic. Let's quickly complete it. B is the magnetic field. What is L? Length of conductor, not the track. And V is also the velocity of conductor. Velocity of conductor. Now, some modifications of this formula is very easy, BLV to remember. These modifications you should know. If I divide EMF by resistance, so I can get the current. So this is the BLV by R becomes the formula for current. Okay. Now we have studied that force in a conductor is equal to BIL. So magnetic field we know. I, current we have calculated here. If you put the value of current, this becomes B square L square V by R. This is the formula. So what is this? This is the formula of force. And you know that power is equal to force into velocity. If power is equal to force into velocity, then you multiply one velocity. So this is the formula for power. One V will be multiplied. So B square L square V square by R. These are the formula. One question we will see from NCERT. Easy question. This topic is very easy, motional EMF. But the formula comes in the exam. It comes in the exam. So it's important. Write it. This you have written. This derivation part from here. Okay, so this question says that an aircraft with a wingspan of 40 meter flies with a speed of 1080 kilometer. Firstly, at this step only, we need to convert 1080. Okay, Zaina, incorrect answer, but at least you are the one only who has tried. Other students have not shared the answers. Zaina, I think just have a look at your calculations. 1080 into 5 by 18. Firstly, you all have to multiply. So this will be 5 into 5400 by 18. So 300. 300 meter per second. Okay. Now length is given as 40 meters. Magnetic field is given as 1.75 into 10 to the power minus 5. Sufyan, your answer is correct. Very good. Now EMF is BLV. So 1.75 into 10 to the power minus 5. Length is 40 into velocity is 300 meter per second. Correct. Yeah, answer is right. Answer is correct. 0.21 volts answer is. Those who have not written, you can write. Just one thing, class. There's a topic known as eddy currents that is now deleted from your syllabus. So no need to study this. This is just somewhere in the previous paper when you're solving. Just for the discussion purpose, we are doing it. You just have to copy it later. Currents which run across blocks or sheets in the form of a whirlpool. If a sheet is there, 2D sheet or a block is there, so the current will travel. They are used in sheets, blocks, the magnetic flux for called currents. So there are lots of applications in induction furnace, electromagnetic dumping, electric brakes, speedometers, and all. So you just have to copy this portion, mention that it's not in your syllabus. We are just discussing it because eddy current term can be used in questions. Okay, before Okay, class, come to induction. Now, what is meant by induction? So, see, in induction also, you have two types of phenomena that you will be encountering. One is a portion where you will see, where you see it is called as self-induction. Other is called as the mutual induction. Now, self, from the term self only, you can identify that this is related to objects or cases where only single involvement is there. Self-inductance means single involvement of what? Single involvement of the loop. Single involvement of the circular loop. So this circular loop, this will be having one single circular loop is sufficient to create a case of self-induction. Now, what is meant by this? This is understood through the concept of the circular coil. Let me just do those. See, this is a circular coil. Okay. Now, suppose magnetic flux. Suppose the magnetic flux here is increasing, or here this magnetic flux is decreasing. Means this is the change in the flux. Now, this can be due to increasing magnetic field. This can be due to decreasing magnetic. Now, this will lead to development of induced current. Okay, this will lead to the development of induced current, whose direction can further be given as minus, plus, or anti-clockwise or clockwise or anything. But this is occurring within the same coil. That is what is called as self-induction. So what is self-induction? Self-induction is a phenomena of production of induced EMF in a coil when a changing current passes through. Same means induced current is produced. Now, after the induced current is produced, you will encounter induced EMF. And again, this induced EMF will be directly proportional to flux. This is the whole concept. Now look at this. When we are talking about induced current, suppose I have closed the switch. There's a battery connected. This is a wire. This is an inductor. Inductor we have not studied because inductor specifically term this will come. I'll tell you. But this is an inductor. This device is an inductor. There is a wire connected and a switch is there. Now when I close the switch from 0 level to the maximum level, current will start increasing. Current has started increasing, flux is further increased. Because there was a flux, then only we had the current also, and this will create increment in the induced EMF. Now, if I open it from the maximum value, the current will go to the minimum, its lowest value. So current will decrease, flux, magnetic field, both will decrease. Here also magnetic field must have increased. And EMF further decreases. So change in the magnetic field, change in current, this portion is important for us to do this. This portion is important. So this is the case what happens within the circuit. Okay, regarding this, I'll tell you, self-induction will try to complete it today. Write it from here. Okay, let's continue further. See, this says we have already studied that EMF is directly proportional to the flux. Now here we will see when we remove the proportionality sign, here you will see that a constant is there. Okay. Now look here. One more thing before this, one step I have missed. See, EMF is directly proportional to phi over time, d phi over dt. Now, here in this example, we have seen that current and flux are linked together. That's what I was telling you, that you have to focus on flux. So flux is directly proportional to current. And now here, when we remove the proportionality sign, we get this constant L. This is known as coefficient of self-induction, or even without this also, even if you have to, if you want to use, you can use and directly call this as self-inductance, directly self-inductance. This is what is the unit. I, you know, it's current, and flux, you know, it's phi, you know, is magnetic flux. Okay. So your phi is equal to Li. From here, inductance is equal to flux divided by the current. Okay. Now see, it says that self-inductance is numerically equal to the magnetic flux when we put the current's value as 1 ampere. If this is 1 ampere, then we can say self-inductance is directly proportional to the magnetic flux. So you can use this equation, you can use this definition. What's the SI unit? C for inductance? 1 volt divided by, what is in the denominator? Ampere per second. So 1 ampere per 1 second. Instead of using this unit, it's better if you use 1 unit is there, which is called Henry. Simply capital H will be used. Use Henry for induction. Self, mutual, koi bhi ho, just use Henry. Dimension C, L is equal to phi by I, which is equal to flux is equal to magnetic field into area by the current. So this is M. For current, we use ampere. So A minus 2 will come. So L square, area L square, T to the power minus 2 per second, and 1 second from here. A to the power minus 2. A is for ampere. This is the dimension. Dimensions for this can be asked. That's why we are discussing. Write it from here.